In this example, I would like to diagonalize the following 3 by 3 matrix. The first row is 3, 2, negative 3. Second row is negative 3, negative 4, 9. And the third row is negative 1, negative 2, 5. Now for those that don't immediately recognize this was a matrix that we found all the eigenvalues and eigenvectors in the appropriate playlist. So from that playlist, we got that lambda equals 0 was an eigenvalue, and we got the corresponding eigenvector of, let's see if I can check my work here. Oh yes, it was negative 1, 3, 1. We also got that lambda equals 2 was an eigenvalue of multiplicity 2, which is why we were able to come up with 2 eigenvectors for this eigenvalue. They were v equals negative 2, 1, 0, and v is equal to 3, 0, 1. We are going to use these to construct our matrix P that we are going to use to diagonalize A. So these are once again our 3 eigenvectors. I'm just going to go with the order of lambda equals 0 and then the 2 for lambda equals 2. So first column will be associated with lambda equals 0. That'll be negative 1, 3, 1. Second column will associate with lambda equals 2, and we'll do negative 2, 1, 0. And then we'll use the other linearly independent eigenvector that we got, which is 3, 0, 1. Now this is where we're going to use the calculator to help us out a bit, because we are supposed to take P inverse times A times P, and we should wind up with a diagonal matrix of eigenvalues, and our prediction is that D is going to be the matrix with 0, 2, 2 on the main diagonal, and zeros elsewhere. So into the calculator, I will be typing in the following. Negative 1, negative 2, 3. Hi, BB. 3, 1, 0. 1, 0, 1. Inverse. Multiplied by matrix A. 3, 2, negative 3. Negative 3, negative 4, 9. Negative 1, negative 2, 5. And then finally we'll multiply that by the matrix P. Oh, cutie pie. Negative 1, negative 2, 3. 3, 1, 0, 1, 0, 1. Now once again, this is where we're going to ask the calculator to help us out a bit. So into the matrix menu I go. We're going to start by editing the matrix A. The A that I have here will be the same as the A that's in here. However, since I just did the eigenvector eigenvalue example using this, we see that the matrix is actually already typed in here. We'll just call that one a nice little bonus. Anybody who doesn't already have that but is playing along at home, feel free to pause the video if you need to. Then as my matrix B, I'm going to type in my matrix P. So matrix P says negative 1, negative 2, 3, 3, 1, 0, 1, 0, 1. So just to make sure everything is in correctly, here's my matrix A, which does look good. And here's my matrix B, which looks good. So here's the part where the calculator is going to do all the work for you. Select B, inverse, multiply that by matrix A, multiply by matrix B, and then here's the part where you cross your fingers real good, because if it works correctly, this should be a diagonal matrix. In fact, it should be this diagonal matrix. Let's see what happens. I press enter. Now, let's talk about this, this thing that just happened on our calculator. So what we have here is first row is 0, 0, 0. Second row is 0, 2, 0. And the third row is your calculator kind of phoning it in and being like, you know what, that's close enough. Once it's accurate to the 12th decimal place, I don't really care what's after that. This number that's represented here, 5 times 10 to the negative 13th, is actually the number 0.0000000000005. Now, normally what takes place is on your calculator, you only see the first 9 or 10 decimal places of something. So if we were to round this off at the 10th decimal place, like we would expect to do so, that'll be 0. Now, calculators use something that's referred to as the Cordic algorithm to calculate things, especially matrix multiplication, as well as trigonometric functions of strange angles. If you're ever interested in looking up how calculators calculate, look up the Cordic algorithm. It'll help explain why things like this happen.